Hello. In the previous video, we talked about closure under vector addition. So let's just remind ourselves what that even means. If you have a subset of Rn, it's called closed under vector addition if whenever you take two vectors in S, which by the way might be the same thing, they might be the same vector, possibly the same vector. But two vectors in S, if you add them, the result, the sum, has to be also in S. When that happens, the set is called closed under vector addition. So we did some examples of sets that are closed under addition, not closed under vector addition, and then we gave an example of a proof that a set is closed under vector addition. Let's talk about a related topic, which is called closure under scalar multiplication. And this is similar to the definition of being closed under vector addition. So we say that a subset of Rn, so a subset S of Rn, is said to be closed under scalar multiplication closed under scalar multiplication if for every v in S and every scalar c, cv is also in S. Okay, so that means that whenever you have a vector in S, every scalar multiple of that vector is also in S. Well, if you take a vector in S, okay, and look at all the scalar multiples, that's a line, right? So what it means is that it can't contain parts of a line. It has to contain the whole line. But let's look at some examples. This was a definition. So please memorize this definition. Let's look at some examples. Let's look at some of the examples above. So before we had S, which is the set of points, the set of vectors xy, such that x is greater than or equal to 0 and y is greater than or equal to 0. So this comma means and. Okay. Maybe I'll just delete this. X is greater than or equal to 0 and y is greater than or equal to 0. So that includes this positive axis and this positive axis. All these vectors, right? So that's S. Is this closed under scalar multiplication? Is it true that whenever you have a vector in S, every scalar multiple is also in S? Well, no, it's not true. This is not closed under scalar multiplication. Because can you find a vector that's in S and the scalar multiple that's not in S? You could take something like, actually any of these arrows I drew would work. You could take something like that, because 1, 1 is in S, but let's say you take C to be any negative number, but negative 5, 1, 1, well that's negative 5, negative 5. That's, what's that? That's this vector, right? That's definitely not an S. So that shows that S is not closed under scalar multiplication. And let's just think about spelling out what it actually means to be not closed under scalar multiplication, right? If a subset is closed under scalar multiplication, if for every v in S and every scalar C, for every scalar C, CV is also in S, what it means to be not closed under scalar multiplication, if you think about the logic, okay, a subset S of Rn is not closed under scalar multiplication. What that means is if there is some vector v in S and some scalar C such that CV is not in S. In other words, it's possible to somehow scale out, to take a vector and somehow take a scalar multiple of that vector and get outside S. Okay, let's look at another example. Let's say that S was the set consisting of all vectors on these two lines. So let's say this is y equals x, and that's y equals negative x. And we take that set S. So in other words, S is the set of vectors x, y, such that y equals x or y equals negative x. Is that set closed under scalar multiplication? What do you think? The answer is yes, it is closed under scalar multiplication. Okay, and the reason is because if you take a vector in this set S, let's say you take this vector, any scalar multiple of that will also be on that same line. So if I took this vector here, any scalar multiple will still be on this line, which is in S. And if I take a vector like this on this other line and take any scalar multiple of that, I will also stay on the line. Okay, so how would we write this out? How would we write that explanation out? Well, if V is in S, where V is xy, then y is x or y is negative x, because V is an element of S. So for any scalar C, okay, V is going to be, CV is going to be CXCY, right? So if y is x, then cy is going to equal cx, so CV is in S. Because remember, it's important to keep in mind that when someone says, the vectors x, y such that y is x or y is negative x, this is saying that x is the name for the first component and y is the name for the second component. So it's saying that the two components are either equal or the second component is -1 times the first component. That's what this is saying. So when you say something like CV is this, okay, or CY is equal to CX, why is CV in S? Because the first and second components of these vectors are the same. Okay. And so that's if y is equal to x. If y is equal to negative x, then, okay, cy is equal to negative cx, right? And so CV is also in S. is again in S. And that's the explanation. That's basically a way of writing down that when you take any vector, if you take a vector on the line y equals x and scale it, you stay on the line because the components are the same. And if you take a vector where the second component is -1 times the first component and scale it, that new vector, the second component, will still be -1 times the first component. Okay, so those are some examples of closure under scalar multiplication. Let's review a little. Is this set S closed under vector addition? So take and this is going out forever, right? Just because this is y equals x, y equals -x. What do you think? Let's go over the answer. Make sure you pause the video and think about it before you continue. So the answer is no, it's not closed under vector addition. S is not closed under vector addition because you can take, actually you can take these two vectors, the ones I just drew. If you add them, you get this vector, which is not an element of S. Okay, but we need to come up with specific vectors here. Not closed under addition because, okay, so what are some vectors that are in S, but when you add them, you get something not in S? How about 1, 1 is in S, right? Because y is equal to x. And, okay, let's think here. -2, 2. Okay, well, that's certainly an S. Okay. So let's just, maybe I'll just write out a little bit more just in case it's not clear. Why is this an S? Because y is x in this case. And -2, 2 is an S because, in this case, because the y value 2 is negative, I mean, it's -2, right? It's -1 times -2. But the sum, which is, if you add them, you get -1, 3. This is certainly not an S. Because, well, because 3 isn't -1. And 3 is also not -1. And that explains why S is not closed under vector addition. So remember, to show that a set is not closed under vector addition, what you have to do is you have to find two vectors that are in S, but whose sum is not in S. Also, I really want to make sure that when you're learning this subject that you get used to this notation and you understand what it means, right? So that's kind of part of the point of this problem, is to help you, is to make sure that you learn how to read this mathematical notation. All right, well, with that, we're ready to move on to the definition of a subspace, which is sort of the meat of this. It's sort of the point behind closure under addition and closure under vector. It's a bit late. I'm getting kind of tired. Closure under vector addition and closure under scalar multiplication. Okay. So with that, we're going to move on to subspaces, which is an important topic. It's an example of something called a vector space. And the vector space is one of the central themes in linear algebra. It's one of the important concepts. And in this series of videos, this first course in linear algebra, we won't go into general vector spaces, but the examples we're going to use of vector spaces are subspaces of Rn. And that's what we're going to talk about in the next video. Thanks for watching.